This is a lecture that I think will be fundamental to our entire course here. And this is a course about science. And science has had a very interesting history because science of the past century and science of the current day are very different. There's always been a progression of beliefs in science. So it's a system. Science comes from a root word in the Greek that means to know. So science is a system or a process of knowing. And it's based on assumptions. So really, what we're doing in science, I know I found this in psychology, that people don't see anything that they don't have an idea about to begin with. And so what happens with our assumptions in science, we see our observations through the filter of our assumptions. Now, it depends on these concepts then, but it is known by observation. Now, we have this idea, or we have had this idea in science, that we're looking at an objective reality. Well, it turns out that that's not really true because we're looking at it through the filter of our concepts and our assumptions. And we only see what we think is there. But that process develops and evolves. And particularly when you expand your concepts, then your observations will evolve. Now back, 250 years or so ago, the idea that was going on in science was it assumed that the observer and the phenomena were independent of each other. This is a picture here of René Descartes. And Descartes thought that you could analyze things. This is like at the roots of analytical science. He was a mathematician and believed that there was some objective reality that was beyond us, that we had no influence over, that we could only maybe observe, but we weren't in the process of observation having any effect on what it was that was going on. And the belief at that time, this is Pierre Laplace, and he thought, he was another mathematician, thought that all things past and future could be determined if you only had the mathematical tools and you had sufficient data, then you could calculate all the outcomes to the end of the universe. And this sort of like was a concept that believed that there was a billiard ball universe, and whatever the prime mover was, whatever like shot the cue ball into the rack, that everything else could be calculated from that moment. And Emanuel Kant believed that, well, first of all, to make things simple enough that you could get your head around it, then he assumed that only the observations of the five senses were real. In other words, if you couldn't see it or hear it, taste it or smell it or touch it, then it didn't exist. It wasn't real. And this was called reductionist science because it reduced the things that we had to consider to just those five parameters. And we didn't have to worry about emotions. We didn't have to worry about ideas or intuitions or imagination or any of those sorts of things. that it was all just a matter of the five senses, that that was the basis of reality, and anything else didn't really exist. It didn't have any reality. Sir Isaac Newton, who really gave science a big impetus, was another mathematician, and he introduced such things as calculus, the laws of motion, and so forth. The idea that there was a law of gravity, and he assumed that knowledge could only be gained via these five senses. And you might say that that belief believed that matter was the cause of everything. Everything stemmed from the elaboration of substance. Now, sort of parallel to that view of science, there's another scientific tradition of holism, and it goes back to Paracelsus or Pythagoras and so forth. But this belief held that the observer and the phenomenon are inseparable, that you couldn't have a phenomenon without an observer, or vice versa. And this is a picture of Johann Wolfgang von Goethe, and this assumes that intangibles like thought and feeling and intuition and cognition can also be known, and they're also real. Rudolf Steiner, which we will hear a few more things about in this course, believed that the inorganic processes oppose. In other words, there's opposite poles in the mineral realm, and the processes occur between those opposites. And also that the organic processes, unlike the mineral processes, the organic processes, what drives them is enhancement. And they grow and they evolve. So that this belief was based on the polarity of substance and the enhancement of life. And this is where we get biodynamics and a number of other things that may influence my presentation in this course. But Rudolf Steiner was, sometimes I call him a biochemist before they invented the word biochemistry. He was a scientist that was so far ahead of his time that we're only now demonstrating a lot of the things that he said that were, well, they were invalidated, maybe even suppressed. They were ridiculed. And so, but we're coming in the progress of the evolution of science to finding that there's a great deal of wisdom behind this. And this is, Steiner assumed that life processes involve this growth and enhancement. So in biodynamics, there's a belief that all is one. Both the innermost and outermost influences participate. And this assumes that patterns provide organization. Patterns are the basis of order developing out of chaos. And that's what gives us life. And we're looking at here an earthly and a cosmic polarity. But within the earthly, there's the seeds of the cosmic. And within the cosmic, there's the seeds of the earthly. And this is an old, I don't know how old this particular symbol is, but it goes way back into the dawn of mankind's history. Now, in modern physics and modern science, this is a picture of Werner Heisenberg. And Heisenberg demonstrated conclusively in the world of physics that the observer and the phenomena are inseparably linked. And Heisenberg's experiments and his mathematical rendering of these demonstrated that it's the very presence of the observer and his or her measuring instruments that is a determining factor in the field of investigation. In other words, a message that was stated in an earlier time of belief on faith, that seek and you will find. That's what Heisenberg proved in the laboratory. What you look for is what you will find. And he did it on this basis, that if you looked for the location of a photon, then you could find out where it was, but then you wouldn't find out what it was doing. In other words, the wave phenomenon of the particle, you'd lose sight of it the more accurately you located its location. So if you found out where it was in its behavior as a particle, well then you'd lose sight of its wave character. So you wouldn't know the amplitude or the wavelength of the wave. If, on the other hand, you go looking for its wave behavior, then you can't find its location anymore. And this proved out to be such a consistent rule. It was called, in German, it was called Heisenberg's theory of indeterminacy. But this got translated into English as Heisenberg's uncertainty principle. And it revolutionized science in the 20th century, back in the early days of the 20th century. And other physicists were saying, well, yeah, we see that. Yeah, it has to be true. But what does it mean? And if you think about this, in its ramifications, it means that we, as observers, by choosing what it is we look for, we're creating the realities we inhabit. Wow. By looking for certain phenomena, we're actually creating those realities. And I had seen this in the world of psychology, that people that have certain expectations, that's what happens in their lives. When you have an expectation that no matter what occurs in your life, that it occurs for a reason, and that there is a plan and there is a value to what happens in your life. And no matter what it is, like my father was stationed on Corredor in the Philippines, and he got polio and got sent back to the States before the garrison, before the World War II broke out, and the garrison that surrendered to the Japanese was barged over to the mainland and marched up the Bataan Peninsula to Changi, and 5 out of 6 of them died on the march, and the rest stayed in Changi the rest of the war. And so he was very lucky that he got polio, or I wouldn't be here. So if you look at it from that point of view, and growing up as a kid, we kids didn't have any inkling that there was anything wrong with being in a wheelchair, because we never heard a word of complaint, and Dad did whatever. He figured out how to do it. Like when we moved from Seattle to Louisiana, because a college education, he was going to send my mother to school to get her college education on his veterans benefits from being a disabled veteran. And college tuition was $25 a semester, and all the textbooks were free in Louisiana, so we moved there. Well, Dad painted the whole outside of our house in order to be able to sell it so we'd have the money to move. And what he did was he worked up a harness for his wheelchair, built a block and tackle and A-frame, and got someone to lean it up against the house, and hoisted himself up, tied off, painted all the way to the ground, dragged that frame over, and painted the whole outside of our house from his wheelchair. No scaffolding, no heavy planks, none of that mess. He did it the easy way. So, you know, we saw that sort of behavior all our lives and had no idea until we grew up, you know, and began to dawn on us that, hey, there were some limitations if you were in a wheelchair. And because we would have been happy to grow up and be in a wheelchair like Dad. So it's like, it's what your expectations are. And life is not necessarily what we think. It is what we think in a certain sense, but it isn't necessarily what we think if we change the way we think. This is a picture here of John Bell, another mathematician and physicist. I'm leaning kind of heavy on mathematics here in the roots of science. But the belief in quantum physics was particles may be local, but waves or patterns are non-local. And in the universe, there's a 0 point. Everything adds up to 0. The universe is in perfect balance at all times. And the coherence and balance, synchronicity, the entanglement, and non-local morphogenic fields, what Bell's theorem, which he published in 1955, was that if you had essentially something here, a particle, but it could be a picture of, say, a piece of land. So this is a picture of that piece of land. There is no other piece of land in the universe that is quite like this picture. It's unique and it's entangled with that piece of land. So it's got the same wave pattern, and the patterns are non-local. So you've got the wave pattern in that picture of that piece of land, and they're inseparably linked, instantaneously, as though the universe had no distance between this and no lag in time or any of those things. And testing this, Bell's theorem, the Apollo astronaut Edgar Mitchell, who was himself had a master's degree in physics, and had also experimented with telepathy and clairvoyance via the research that J.B. Rhine did at Duke University in North Carolina. And Rhine developed this system of Rhine cards that had squares and circles and triangles and stars and crescents and whatnot. And they had different colors. And so you had a checklist with the stars and crescents and squares and circles and things, and of the different colors. And these experiments, one person in one location would turn over the card, and the other person linked to them by thinking the same way, would tick the box on the sheet of whether it was a yellow square or a blue circle or a red crescent or whatever. And they did this experiment with Mitchell on the moon and his counterpart at Houston Ground Control, and the telemetry of the rocket, I mean, you know, the space capsule and Houston Ground Control were synchronized, and they found that each time the card was turned over, the counterpart checked the box for that card without the time lag that radio takes to go from the moon to the Earth. In other words, it takes about 1.5 seconds time lag. It's worse than your satellite dish time lag. It takes a little bit of time for the signal to go from the moon to the Earth. But it didn't take that amount of time. It was just a matter of how fast you could tick the box, which is considerably faster. And so it demonstrated the validity of Bell's theorem. Now, this lady here, Olive Whitcher, she was another mathematician, and I've got a copy of her book, The Plant Between Sun and Earth. And it's got, we'll see some of them in this course. She did a bunch of pastel drawings of plants and also of geometrical forms, three-dimensional or possibly more dimensionals, but she did them on paper and represented it in perspective. But the whole idea that there are morphogenic fields that arise as archetypes out of a complementary geometric systems. She said, oh, simplest geometric form, which is a circle, can be described from its context, and it can also be described from its content. Now, we're used to saying the formula for the circumference of a circle is 2 pi r. Well, the radius is the distance from the center of the circle to its circumference. And if you rotate that through 360 degrees, which pi is a function of that, then you will get the circumference of the circle. But that's describing the circle from its center, from its content. But if you took tangent lines and you touched the circle with a line that was going to infinity in opposite directions, that you could also describe the circumference of the circle by a series of tangent lines rotating around its outside, the outside of the circumference of the circle, which theoretically the circumference has no breadth. It's the same circle at the circumference, because it's not a wide. Circumference doesn't have any width as a line. So and what Rudolf Steiner said is that we won't have an adequate mathematics of life, of living organisms, until we use both of these complementary geometric systems to describe it. We have to describe living organisms from their context as well as their content. Just think about it. Where you are in life is a measure of your context. Your life would have no meaning if you weren't surrounded by the world and the cosmos around you. So the context is what gives your life significance. And we wouldn't have an adequate view of what's going on with anyone or any living organism at all unless we view it in its context as well as looking at its content. This is the representation I just spoke about, a point-wise circle and a line-wise circle. And you can see it's the same circumference. And these lines here are going through each of these points. And we're looking at it in both ways at once in this course. And that's the way quantum physics looks at things too. So there we have the particle is based on the content. It's focused on the center. But the wave is focused on the content. And in physics, it's impossible to separate the wave and the particle phenomena. Every particle has a wave component. Every wave has a particle character. So this is the old Newtonian physics, analytical physics, and this is quantum physics, and it's a holistic view of the universe. Okay, how do I fit the string theory into this? We're going to have to do that in a later lecture or outside of class, and I've got a section there on the periodic table and that sort of thing, and it will be a beneficial aid in explaining this, but it's too hard to answer that question in this class. Just keep it in mind. Anyone who doesn't know what string theory is, ask me after class. Now, in Olive Whitcher's drawings, this is some of Olive Whitcher's drawings, and she's looking at the polarity that's going on in plants and out here in the environment as having a lime characteristic, a polarity of lime, and this is calcium, primarily calcium, but also magnesium and potassium and sodium are major cations. And this is the silica side of things. There's a polarity between charge and balance. So silica is a perfectly balanced, it's a non-charged or non-polar type of element. So in the paper disc chromatography, in this book here that Alistair brought, and you may have a chance to look at it, there's all of the siliceous non-polar chemistry in the picture goes to the edges. It doesn't stick to the paper. Whereas all of your charged elements, your lime elements, are sticking somewhere radiating out from the center. So your non-charged chemistry goes to the boundaries, and the charged chemistry is what's held within. So these lime forces are radiating out in these chromatograms from the center, but the silica forces are dealing with the surroundings. So anyone who has a chance to look through Alistair's book there on paper disc chromatography will see these two polarities in every chromatogram. Now there has to be, in living organisms, and in the growth of plants, and for that matter in the life of animals, there's a dynamic interplay going on between the lime and the silica polarities. So you've got the lime polarity and the silica polarity here that interact. And that's what Olive Whitcher was representing in this drawing. And this is how it works in the plant. So you have this sort of dichotomy of activities. So you've got things that spread on the horizontal and things that push, you might say, on the vertical. So it's what's going on in plants is a dynamic interplay between these two polarities. And if one polarity is lacking, then it will affect the other one. And so in dealing with the activities that are going on in plants and animals, like on a pasture, your clovers, your legumes, are on the lime polarity, and your grasses are on the silica polarity. And if all you had was grass, or all you had was clover, then you wouldn't have that balance between them, and it would limit the dynamic interplay going on between the lime and the silica polarity. Now, self-similarity gives rise to order. And in mathematics, there's this very peculiar number called phi, or the golden mean. And like pi, phi is a transcendental function, meaning that it's like a wave, and it cycles around a certain value but that value can only be approximated by a ratio between two numbers. But actually, both pi and phi they're irrational numbers. You can't reduce them to a ratio between two numbers. They're non-repeating decimals. And the further out we calculate the values of either pi or phi, then we get these non-repeating decimals. Any repeating decimal can be expressed as a ratio between two numbers. But if it can't be expressed as a ratio between two numbers and is an irrational number, it will be a non-repeating decimal.
So how does it relate to that shield?
Okay, what's happening here is every division is 1.61803 times the previous one. So phi, see, this here is 1.61803 greater than this. But because of the self-similarity, then this one here is 0.611803 of what this one is. And if you went to this one, then, sorry, I'm getting myself confused. If you went from this one to this one, see, if you go it higher, then this is 1.61803 times this one. This one here, though, is 2.61803. And this one, the third one away, is 3.61803, and so forth. So that relationship there is based on phi, and it's a self-similar number, the only truly self-similar number that we have in mathematics. So like pi, it's a unique number, and it's one of those things that gets into the basis of the universe. The universe just has that property of self-similarity at that number, which isn't a number that we could ever reduce to a complete number. It's a transcendental number, which means it transcends anything that we can look at as finite. We can't reduce it to something that we can say, this is it. This is approximately it, is the best we can do. So here we're looking at a way of looking at the universe where we're looking at matter, and matter descends into chaos. Matter isn't alive. Entropy rules matter. In the substance realm, everything is running down and becoming more chaotic. But in the life realm, and I call this the etheric realm, this goes back to an earlier expression of what ether is, goes back to Paracelsus and to Goethe, rather than the physicists of the 19th century who thought that ether was a medium for propagation of light waves, and when they found no such thing existed, then they said, oh, well, there is no ether. And Einsteinian physics was based on the belief that there was no ether. And so we're going to have to reconcile Einsteinian physics with quantum physics. And that hasn't been done to the satisfaction of either the Einsteinian physicists or the quantum physicists. So in physics today, there's like two, you might say, schools of thought. And although there's a great deal you can do with either one, we're still at the point in the world of physics of not being able to reconcile those two beliefs. But what we're going to deal with in this course is the quantum belief. And in quantum physics, syntropy is where order arises out of chaos. And it trends in the direction of greater concentration. So in the development of a cloud, the moisture in the atmosphere has to coalesce into the cloud. It has to gather up into the cloud. If it didn't, we would never have any rain. And of course, we realize that there is rain, but the important thing for us is how do you get more, or how do you get less? Well, if we can apply quantum physics to the development of clouds, then we can intensify the degree to which they gather up the moisture in the atmosphere to the extent that we get rain. And as we know, Chabry has participated in these ceremonies out in Four Corners, which isn't exactly in Utah, isn't exactly in Colorado, isn't exactly in New Mexico or Arizona. It's at the point where those four states meet. It's called Four Corners. And there's a Hopi Indian reservation out there in the desert. And they're living where no one else knows how to live. They're a peaceful tribe of Indians, and they don't want any strife with their neighbors. So they have found out how to make rain on their corn crop and their pumpkins and things every summer in the middle of a desert where nobody else knows how to live, and everyone leaves them alone. Nobody covets their territory because nobody else could do anything with it. But they know how to make it rain, and they haven't missed in the last 4, maybe 5 or 6,000 years, because they didn't have government aid agencies back then, and nobody was going to come to rescue them. But they've been very consistent. They know how to make rain. And in this course, I hope that I will shed some light on those processes, because this is an Australian experience that everyone gets a taste of, that there's times when it gets real dry and it just won't rain. And one of the reasons I'm in Australia is because I got so confident where I lived in Georgia. In the midst of drought years, my side of the county would have rain, and I gave away my irrigation system. So I think there's a to it. When we look at the elements, we're looking at, in a classical sense, back in the Greek classical sense, we're looking at fire, air, water, and earth. Now, I know we have used the word element today to talk about the atomic structure of different elements in the periodic table. And we've got over 90-some elements in the periodic table, actually over 100 when you consider some of the synthetic elements. But these are tangible materials. We can pin down their locations. But in terms of the waveform, the pattern of the element, then we've got the ethers. And the ether associated with fire it involves fruit, and it's the warmth ether. Fruit ripens mostly in the warmth. But things bloom in the light. So the blooming season is basically the season of the strongest light, which would be the spring, but this would be the summer, where it gets very warm. But the summer really starts with the summer solstice, and the light is decreasing even though the warmth is increasing. Then we have the leaf activity, and this is where it expresses it in the plant, and this is the tonality or chemistry of the water. It's the process that's going on in water. And this here, the root process, is what's going on in the earth element. And so this is a sugar beet to express that carbon life nature, the solid carbon structure. And so we're all carbon-based life forms. So it's called the life ether.